Okay. Now, if you have lots of particles, okay, moving in 3 dimensions, then it can be shown that the pressure would be equal to 2/3 times the sum of all the translational kinetic energy divided by the volume. Okay, so sum of all the translational kinetic energies. What do we mean by translational kinetic energy? That's 1/2 mv squared, okay? Kinetic energy, we say, is 1/2 mv squared. When we talk about that in general, we mean the translational kinetic energy. I'm specifying translational kinetic energy here because a molecule can actually have more than just translational kinetic energy. So what we call the kinetic energy of the molecule is the sum of a translational energy and energy due to rotation and vibration. If you want to see, let me show you an animation that shows you the additional um, kinetic energy due to motion of the molecules. This is an old movie that you can find at the Internet Archive, archive.org. Okay, just look for, do a search for Molecular Motion, second edition. When you get to at the 551 mark, there's an animation there that shows you the differences between translational motion, rotational motion, and vibrational motions. So translational motion, as you'll see here, is described as motion from place to place, okay? Motion through space. And then rotational motion would be sort of like the tumbling motion of the molecules. And then within the molecule itself, you'll have what are known as vibrational motions. So let me just play that segment of the video. This is a very interesting video and very educational. You should really watch it. I have a link to this in the Moodle course site. Okay.
Here in very slow motion are models of several kinds of gaseous molecules undergoing translation, that is, motion from place to place. In addition, most of the polyatomic molecules have a further kind of motion, rotation. And close examination shows still another kind of motion, vibration. Rotation and translation involve only molecular tumbling and simple motions through space. But vibrational motions can appear complicated, as in this model.
Okay, that should be enough. All right. So anyway, what we call translational kinetic energy is kinetic energy that's associated with motion, simple motion through space. Okay, that doesn't include the total kinetic energy for a molecule has to include not just translational motion, but rotational kinetic energy to the tumbling. You can say tumbling motion of the molecule, and you have rotational, and you have energy due to the vibration. I mean, kinetic energy due to the vibration of the atoms within the molecule. Okay. So anyway, if you compare this equation right here, this is something you can derive from, like I said, applying physics to a collection of molecules. So we can calculate the pressure that they would depart on the wall. Okay, it's related to their translational kinetic energy. Let's compare this equation with the ideal gas equation, which says P is equal to nRT over V. Remember, ideal gas law says PV equals nRT. So if you compare these two, you can see that you can solve for the sum of the translational energies, okay? And it should be a simple matter of showing that when you solve for the sum of the translational kinetic energies, it's going to be equal to 3/2 times n times r times t. So this equation then gives us now a way of interpreting what temperature is, okay? So what's temperature? You can see it's related to the translational energy. And you'll notice if you divide this by the number of moles, okay? Let's see. If you divide both sides by the number of moles, okay, you can see temperature is sort of like it's like averaging your translational kinetic energy, right? The total divided by the actual number of molecules. So temperature then we say is a measure of the average kinetic energy, average translational kinetic energy of the molecules. So temperature is a measure of the average translational kinetic energy. So total energy divided by number of moles, that gives you 3 halves RT. This is the translational energy of 1 mole of molecules. Okay? So that's per mole. So if you divide that by Avogadro's number, okay, you can see 3 halves times kT. K is R divided by Avogadro's number. That's called the Boltzmann's constant. And so the average translational kinetic energy, that's per molecule, is 3 halves kT. So temperature is, you say, 2/3 times K, 2/3. We solve for T here, you can say temperature is 2/3 K times the average translational kinetic energy. So that means the faster, the higher the average kinetic energies of the molecules, the higher the temperature. Okay, and as I've mentioned, there's atoms, molecules do have additional kinetic energies due to vibration and rotation, whereas atoms only have translational kinetic energy. All right. So here's a question. Which has more kinetic energy? A molecule with a mass of 32 atomic mass units moving at 300 meters per second, or that's a molecule, or an atom with a mass of 32 atomic mass units, same mass, moving at 300 meters per second. Which one has more kinetic energy? The answer is A. Why? Because they have the same translational kinetic energy. It's going to be the same, right? But the molecule has extra energy. Translational kinetic energy plus rotational kinetic energy plus vibrational kinetic energy. So we say the molecule would have more kinetic energy total. In terms of just translational energy, just movement from place to place, simple movement from place to place, they have the same translational kinetic energy because they have the same mass, the same speed. Okay? So let's calculate the translational kinetic energy per mole of gas particles at room temperature. What was the formula? Yeah, translational kinetic energy is 3 halves and RT, that's the total. So per mole, that would give you 1 mole for N right there. So 3 halves times 1 mole, okay, times R, which is 8.314 joules per Kelvin per mole. That's the value of R, joules per Kelvin per mole. And the temperature is 298 Kelvin. So Kelvin cancels out, mole cancels out. That gives you the translational kinetic energy in joules of 1 mole. So let's solve for that. 3 halves. 3 divided by 2 is 1.5. Make this in regular notation. Times 8.314 times the temperature of 298. That's 3,716 joules. Okay. Let me do this. I'm going to calculate RT first because this is something you'll see a lot. Okay, so 8.314 times 298, that's 2477. Okay, so that's going to be 2.48 if you're doing 3 sig figs, 2.48 kilojoules. This is 2.48 kilojoules per mole. Okay, so multiply that by 3 halves and 1 mole. That would be equal to times 3 divided by 2 times 1.5, so that's going to be 3.72 kilojoules per mole. Okay. Try to remember this number because you'll see that a lot. That's the value of RT at room temperature. And there's a lot of formulas that you'll encounter that has RT in it, so it's a good number to remember. It's about 2.5 kilojoules per mole. Okay, so 1.5 times that would be your translational kinetic energy per mole. That's the total kinetic energy of 1 mole of gas molecules. Right. So which sample of gas has more translational kinetic energy at 298 Kelvin? 2 moles of neon, 1 mole of H2, or is it the same for both? Let's see. What's a formula for translational kinetic energy? It's 3 halves nRT, right? We're just dealing with translational kinetic energy here. So, same temperature. This is n equals 2. This is n equals 1. So, which one has more translational kinetic energy? Neon will have more translational kinetic energy. Okay? Bigger n. Same T, same RT, same 3 halves here. So, bigger the n, the more translational kinetic energy. How about this question? Which sample has more translational kinetic energy per mole? So, it doesn't matter how many moles you're given. You just compare 1 mole. You're really just being asked to compare 1 mole versus 1 mole. So, translational kinetic energy per mole is 3 halves nRT divided by n if you want it per mole. So it doesn't matter what n is, right? So that n cancels out. So 3 halves RT is the translational kinetic energy per mole. Since we're looking at the same temperature, same T, per mole value of translational kinetic energy would be the same. Let's calculate the average kinetic energy of helium atoms at 300 Kelvin. So kinetic energy is 3 halves nRT. That's a total, right? If you want per mole, you divide by number of moles, right? That will give you per mole. If you want per atom, you divide by Avogadro's number, okay? That will give you the average kinetic energy. So I'm going to put this in this bracket symbol right here to say that's the average kinetic energy per atom. Now, R over Avogadro's number is also known as Boltzmann's constant. So if you remember, we said the formula for that is 3 halves kT, or K sub BT. Right? So let's plug in the numbers. 3 halves. R is 8.314 joules per Kelvin per mole, divided times the temperature of 300 Kelvin. Let's just treat that as exact. And our Avogadro's number is 6.022 times 10 to the 23rd per mole, atoms per mole. So per mole cancels out, Kelvin cancels out. That gives you the answer in joules. Okay? So that would be how much? You can plug in those numbers. Let's see. If you remember, RT was about 2.5 kilojoules at room temperature, right? So you could do it that way and then divide by Avogadro's number. So this is about 2,500 joules in the numerator. Let's see, 8.314 times 300. You can see the numerator is about 2,500 joules. It's about 2.5 kilojoules. Okay, divided by 6.02 times 10 to the 23rd. That's this number right here. So 4.1 times 10 to the negative 21. So 3 halves times 4.1. 4 times 10 to the negative 21. Multiply that by 1.5. That gives you 6.21 times 10 to the negative 21 joules. Okay? So that's kind of a small number in joules. That's of course because you're dealing with with energy on a per atom basis. So single atom's not going to have much energy. All right. Which sample has a higher average kinetic energy? 2 moles of helium at 298 Kelvin, a mole of O2 at 298 Kelvin. So you're talking about average, so that means on a per atom or per molecule basis. So this is on a per particle basis. So average translational kinetic energy will just be 3 halves kT. It doesn't matter how many you have, you can ignore how many moles you have, right? Talking about an average. Talk about an average, you just divide by the however many you have. So ignore how many moles you have. So really just comparing helium and O2. They're going to have the same translational kinetic energy because they have the same temperature. So which one is the higher average kinetic energy? They have the same translational kinetic energy, okay? But O2, okay, so they're going to have the same average translational kinetic energy, but O2 has, in addition to translational kinetic energy, rotational and vibrational kinetic energy because that's a molecule. Whereas helium is an atom, it won't have vibration and kinetic. It will not have vibrational and rotational kinetic energy. So the answer would be B. Okay?